Assalamualaikum and good day to all of you. Let us continue our discussion on Chapter 2. Section 2.3, the last section in Chapter 2, discusses another type of first-order differential equation known as the exact equation. Let us begin by looking at the definition of an exact equation. A first-order differential equation of the form m of xy dx plus n of xy dy equals to 0 is called an exact equation in a region omega if there exists a function f of xy such that del f del x equals m of xy, del f del y equals n of xy for all xy in omega. Okay, the definition says that suppose there is a region known as omega, and in that region there exists a function f of two variables x and y. Now, if you evaluate the first partial derivative of f with respect to x, and it turns out to be exactly equals to the function m of xy, and if you evaluate the first partial derivative of f with respect to y, and it turns out that it is equals to the function n of xy, for all xy in the region omega, then we say that this first order differential equation of the form m of xy dx plus n of xy dy equal to 0 is an exact equation. Consider an exact equation which is in the form of m of xy dx plus n of xy dy equals to 0. Now, since this equation is exact, therefore, by definition, m of xy is equals to del f del x and n of xy is equals to del f del y. Now, substitute del f del x into m and substitute del f del y into n so that this equation can be rewritten as del f del x dx plus del f del y dy equals to 0. Then divide this whole equation by dx to get del f del x plus del f del y dy dx equals to 0. Now notice that this left hand side is exactly equals to the first derivative f of xy with respect to x. Okay, so this is an ordinary derivative of f of x with respect to x, and we know that these two expressions are equivalent based on the chain rule. Okay, now to eliminate the derivative on the left side of this equation, we need to integrate the left side with respect to x, and we also integrate the right side with respect to x. So the integration of the left side with respect to x gives the function f of xy, and the integration of 0 with respect to x gives the constant c. So in other words, that when we solve this exact equation, the final solution will be expressed in the form of f of xy is equals to a constant c. So this is the general solution of the exact equation. Test for exactness. Theorem 2.1. A first-order differential equation in the form of m of xy dx plus n of xy dy equals to 0 is exact if and only if del m del y equals to del n del x. Okay, now this theorem says that we can know whether this equation is exact or not by evaluating the following. Evaluate the first partial derivative of m with respect to y, and evaluate the first partial derivative of n with respect to x, and see whether these two results are equal or not. If they are both equal, then we conclude that this given first-order differential equation is an exact equation. Determine whether the given differential equation is exact. The first problem, x cubed plus y cubed dx plus 3xy squared dy equals to 0. Now let us compare this given differential equation with the general form of a first order differential equation, which is m of xy dx plus n of xy dy equals to 0. The function m is the coefficient for the differential dx, and the function n is the coefficient for the differential dy. Now let us compare between these two equations. So we identify the function m as x cubed plus y cubed, and the function n as 3xy squared. Now let us determine whether this equation is exact or not by evaluating the following. we find the first partial derivative of m with respect to y, in other words, find del m del y, and find the first partial derivative of n with respect to x, which is del n del x. When we want to find del m del y, we are treating y as the variable and x as a constant. In other words, when we differentiate x cubed with respect to y, the answer will be 0 because this is considered as a constant. When we differentiate y cubed with respect to y, the answer is 3y squared. So 0 plus 3y squared gives 3y squared. For the function n, we find del n del x. In other words, we are treating x as the variable and y as a constant. So if n is 3xy squared, therefore 3 is a constant, y squared is also a constant, x is the variable. So when we differentiate x with respect to x, the answer is 1. 1 multiplied by the existing constant, which is 3y squared, and therefore del n del x is equals to 3y squared. So it seems that del m del y is equals to del n del x, which is 3y squared, and therefore we conclude that the given equation is an exact equation. Second problem, 1 plus ln x plus y over x dx equals to 1 minus ln x dy. Okay, now ln x, that means you are assuming here that x has to be positive because ln of negative number is undefined. Okay, so here we assume that x is positive. Now to determine whether this equation is exact or not, it's important that we rewrite this equation in the general form m of xy dx plus n of xy dy equals to 0. In other words, we need to shift this part of the equation to the left side, so that we get 1 plus ln x plus y over x dx minus 1 minus ln x dy equals to 0. The next step is to identify the m and the n. The function m is the coefficient for the differential dx, which is 1 plus ln x plus y over x, whereas the function n is the coefficient for the differential dy, which is negative 1 minus ln x, and if we open the bracket, it will be negative 1 plus ln x. Now let us determine whether this equation is exact or not by finding del m del y and del n del x. When we say del m del y, we are differentiating the function m with respect to y, treating x as a constant. So when we differentiate 1, a constant with respect to y, the answer will be 0. Differentiate ln x, which is a constant. When you differentiate, the answer is 0. When we differentiate y over x with respect to y, the answer will be 1 over x. For the function n, find del n del x, we are considering x as the variable and y as a constant. Okay, so when you differentiate negative 1 with respect to x, the answer will be 0 because this is just a constant. And when you differentiate ln x with respect to x, the answer is simply 1 over x. So it seems that del m del y is equal to del n del x. Both are equal to 1 over x. And therefore you conclude that this given equation is an exact equation. Example, find the value of k so that the given differential equation is exact. In this question, we are asked to find the unknown k appearing in this equation, which is given in the form of 3x squared plus 2y squared dx plus kxy plus 6y squared dy equals to 0. So to find this unknown k, firstly we identify the function m and the function n. Okay, the function m will be the function which is the coefficient for the differential dx. That means m is 3x squared plus 2y squared. And the function n is the coefficient for the differential dy. In this case, n of xy is kxy plus 6y squared. Now let us determine the del m del y as well as del n del x. When we find the first partial derivative of m with respect to y, we are regarding y as the variable and x as a constant. So when we differentiate 3x squared with respect to y, the answer will be 0 because this term is just a constant. When we differentiate 2y squared with respect to y, the answer is 4y, and therefore del m del y is equals to 0 plus 4y, which is the same as 4y. For the function n, we differentiate or we find the first partial derivative of n with respect to x, we regard x as the variable and y as a constant. So when we differentiate the first term with respect to x, the k and the y, they are both constants, whereas x is a variable. Differentiate x with respect to x, the answer is 1. 1 multiplied by the constants, and so for the first term, del n del x is equals to ky. But for the second term, since 6y squared is regarded as a constant, when you differentiate this constant with respect to x, the answer is 0, and therefore del n del x is ky plus 0, which is the same as ky. Now we are told that the differential equation is exact. Since this is exact, therefore it fulfills the criteria that del m del y is equals to del n del x. In other words, for y is equals to ky, and from here we can know the value of the k is equals to 4. Second problem, 2xy plus 3 ln x dy plus y squared plus ky dx equals to 0. Okay, here we again assume that x is positive because ln of a negative number is undefined. Determine the function m and the function n. Now firstly, we can rearrange in the form of m of xy dx plus n of xy dy equals to 0. Okay, so here we say that m is equals to y squared plus ky over x, and n is 2xy plus 3 ln x. Evaluate the first partial derivative of m with respect to y. Now differentiate y squared with respect to y, the answer is 2y. Differentiate ky over x with respect to y. Take note that k is a constant, 1 over x is also a constant, so k over x is a constant. When you differentiate y with respect to y, the answer is 1. 1 multiplied by the existing constant k over x, so the answer is k over x. And therefore del m del y is 2y plus k over x. For the function n, when you differentiate or find the partial derivative of n with respect to x, x is the variable and y is a constant. Differentiate 2xy with respect to x, 2 is a constant, y is a constant. Differentiate x with respect to x, the answer is 1. 1 multiplied by the constant, the answer is the constant, which is 2y. Plus, for the second term, differentiate 3 ln x with respect to x, the answer is 3 times 1 over x. In other words, it is 3 over x. Okay, so this is the del n del x. Now, since this equation is exact, therefore del m del y must be the same as del n del x. Okay, 2y plus k over x is equals to 2y plus 3 over x. So this implies that k is equals to 3. Let us now learn the procedure for solving exact differential equations. Given a first-order differential equation expressed in the form of m of xy dx plus n of xy dy equals to 0. Now, to solve this equation, the first step is to ensure that the equation is an exact equation. So we need to perform the test for exactness, which is find del m del y and find del n del x. If they are both equal, del m del y equals to del n del x, then we say that this given differential equation is an exact equation. If it is an exact equation, then we proceed to step number 2. If exact, then there exists a function f of xy for which del f del x is equals to m of xy and del f del y equals to n of xy. Okay, so by definition of the exact equation, del f del x is defined as the function m and del f del y is defined as the function n. So this function f is the unknown function that we need to solve. Step 3. Find the unknown function f of xy. In other words, in this step, we are going to determine the solution for the exact equation, which is in the form of the function f of xy. So to find f of xy, we can apply one of the following methods, method A or method B or method C. The textbook that we are using discusses method A and method B, and there are several steps that we need to execute in order to apply either method A or method B. Now take note that in the textbook, for method A, part E, it is written as then substitute the answer in part A. Now this is a mistake, this is a typo. Actually, the correct statement would be then substitute the answer in part B. Okay, so to replace part A as part B. Similarly, for method B, part E, please correct the mistake. The statement says in the textbook, then substitute the answer in part A. Actually, it should be in part B, not part A. Okay, so please replace this part A into as part B. Step number 4 is to write the solution in implicit form. Okay, so once you've got the solution for the exact equation, we need to write it in the form of f of xy equals to a constant c. In this presentation, I'm going to focus only on method C. So there are several steps that we need to execute in order to perform this method C. The first step is to perform step B of method A, which is find f of xy by evaluating the integration of m with respect to x. And the result will be added with a constant in terms of y, call it as g of y. The second step is to perform step B of method B. So if you look at the previous slide, step B of method B is where we find f of xy by evaluating the integration of n of xy with respect to y. And after we have integrated this, we are going to add it with a constant in terms of x, and in general we call that constant as h of x. The third step is to merge the two resulting expressions from steps 1 and 2 above. Okay, so merge these two results to obtain the desired solution of f of xy equals to c. And take note that when we merge the two expressions, write down repeating terms only once. Okay, so these are the steps for applying method C. Example 2.17. Solve the exact differential equation 6xy plus 1 dx plus 3x squared plus 2y dy equals to 0. So we are going to solve this differential equation, but firstly let us confirm that this equation is an exact equation. Okay, so let us determine the function m, which is the coefficient for the dx. M is 6y plus 1. And n is the coefficient for the differential dy. In this case, n is 3x squared plus 2y. Okay, now let us test for exactness. Find del m del y and del n del x. And it seems that both of them are equals to 6x. So since del m del y is equals to del n del x, and therefore the given equation is said to be exact. Now we know that the equation is exact. Let us solve the exact equation by performing the following steps. Okay, let us firstly find f of xy by integrating m with respect to x. Now this is step B of method A. Now substitute m by 6xy plus 1 in this integrand. So integrate 6xy plus 1 with respect to x. So this is a partial integration where x is the variable and y is a constant. So when we integrate 6xy with respect to x, 6 and y, they are both constants. So only integrate x with respect to x. Integration of x with respect to x is x squared over 2 multiplied by the existing constant 6 and y. Integrate 1 with respect to x, the answer is x, and we need to add a constant, and that constant we know is in terms of y, so we write it as g of y. Okay, so in other words, we write down f of xy as 3x squared y plus x plus g of y. Now we can also use other alphabets to represent this function in terms of y. We can also find f of xy by evaluating the integration of n of xy with respect to y. Now this is step B of method B. Substitute n of xy into this integrand. So integrate 3x squared plus 2y with respect to y. This is partial integration. where y is considered as the variable and x as a constant. So for the first term, 3x squared is just a constant. Integrate with respect to y, so we multiply this constant by y. Integrate 2y with respect to y, the answer is 2y squared over 2. Now since we have considered x as a constant, so we have to add a term indicating that x is a constant, so we write that as h of x. Again, we can use other alphabets to represent this function in x. We don't have to use h, you can also use alphabets other than h. So in other words, f of xy is 3x squared y plus y squared plus h of x. So these two are the solutions for the exact equation, and they should be equal to one another. If we evaluate the function f of xy by using this method, we have the unknown in terms of y, whereas if we evaluate the function f using this method, we have the unknown in terms of x. So let us merge these two results together to get the solution for the exact equation. So f of xy, okay, is equals to, for the first term here, for this function f, is 3x squared y plus x plus a function in terms of y. Now, for the function in terms of y, is actually this y squared. This is the function in terms of y. Now, if you look at this part here, f of xy involves a function in terms of x. So this function in terms of x is actually this term here, which is solely in terms of x. So in other words, we say that f of xy is 3x squared y plus x, okay, which is referring to this h of x, plus g of y. Now g of y is this y squared. Okay, so we have merged these two results together to get the solution for the exact equation. And remember in our earlier discussion that the solution of the exact equation is always in the form of f of xy is equal to c, and therefore the final answer is f of xy is equals to 3x squared y plus x plus y squared is equals to a c. Example 218, show that the following differential equation is exact, then solve it. So this is the given equation. Now we want to show whether this is exact or not. So the first step is to shift this term to the left side to get the following form. And then we identify the function m and the function n. So m is x plus 3y over x, and n is negative 5 plus ln x cubed. But ln x cubed by law of logarithm is the same as 3 ln x. Now find del m del y. Okay, in this case, the answer is 3 over x. And find del m del x, which is also 3 over x. And since del m del y is the same as del m del x, so we conclude that the given equation is exact. Now let us solve for the function f. Now f of xy is equal to the integration of m with respect to x. Okay, now m is this function x plus 3y over x. So integrate this function with respect to x, where x is considered as the variable and y as the constant. So integrate x with respect to x, the answer is x squared over 2. And integrate 3y over x with respect to x, and take note that 3y is just a constant. So integrate 1 over x with respect to x is ln x. Okay, and then we add the constant term in terms of y. We can also find f by integrating n with respect to y. Now substitute n as negative 5 plus 3 ln x. So integrate this function with respect to y, where y is the variable and x is a constant. So integration of negative 5 with respect to y is negative 5y. Integrate 3 ln x with respect to y. Now take note this is just a constant. So when you integrate this constant with respect to y, you multiply this constant by y. So it will be 3y ln x. And add another term which denotes the function expressed in terms of x. So we write it as h of x. Remember, x is a constant. So these two are actually the results of the exact equation, but for the first one, the function f contains the unknown g in terms of y, and for the second one, this f of x has the unknown h in terms of x. But both have the same term 3y ln x. So if you look at the first function f, the g of y, the function in terms of y is actually referring to this term here, which is negative 5y. This is a function in terms of y alone. And for this function f, there is a term h of x, which actually refers to this term here, which is expressed in terms of x alone. Okay, so h of x is x squared over 2. So now we can write the solution for this exact equation by merging these two results. So the solution of the exact equation can be written as f of xy is equals to x squared over 2 plus 3y ln x. Okay, so both has 3y ln x, and x squared over 2 here is referring to this h of x minus 5y. So minus 5y is referring to this g of y. So the solution for the exact equation, as we know, must be expressed in the form of f of xy equals to c. Therefore, the final answer is f of xy is x squared over 2 plus 3y ln x minus 5y is equals to c. Example 220. Solve the following initial value problem. X squared plus sin y dx plus x cos y minus 2e to the power of 2y dy equals to 0. Y of 2 is equals to 0. So this is a differential equation accompanied by an initial condition. So the whole set of problem is known as an initial value problem. So let us firstly solve this differential equation. We are going to test whether this equation is exact or not. We identify m as x squared plus sin y and n as x cos y minus 2e to the power of 2y. To test for exactness, we evaluate partial n with respect to y and partial derivative of n with respect to x. And it seems that both have the same result. Del m del y is cos y and del n del x is also cos y. And since these two are equal, we conclude that the equation is exact. Now let us solve the exact equation. Firstly, we evaluate f of xy by integrating m with respect to x. That is, we integrate x squared plus sin y with respect to x, where x is considered as a variable and y as a constant. So integrate x squared with respect to x, the answer is x cubed over 3. Integrate sin y with respect to x, the answer is x sin y, because sin y is just a constant. So multiply the constant with x plus a g of y. Next, we are going to find f by integrating n with respect to y. And substitute n as x cos y minus 2e of 2y with respect to y. Okay, take note that here we are treating y as a constant, as the variable, and x as a constant. So x cos y, x is a constant, integrate cos y with respect to y is just sin y, minus, integrate 2e of 2y with respect to y. When we integrate e power of 2y with respect to y, the answer is e to the power of 2y divided by 2, so the 2 cancel, and therefore the answer will be just negative e to the power of 2y, and then we add another term, we write it as h of x. Okay, so these are the results for the function f of xy. Now we're going to merge these two results together to get the solution for the differential equation. Okay, so both have the term x sin y. Okay, and this function f contains the unknown function h in terms of x, which is actually this term x cubed over 3. Okay, so this is the function in terms of x alone, and this function f contains the function in terms of y alone, which is actually this part here, negative e to the power of 2y. So let us merge these two results together to get the solution for the exact equation. So f of xy is equals to x cubed over 3. Okay, x cubed over 3, which is actually referring also to this h of x, plus x sin y. Okay, both has x sin y, minus e to the power of 2y, minus e to the power of 2y, which actually refers also to this g of y. And we know that the solution of the exact equation is always in the form of f of xy equals to a c. So the final result is as this one here. F of xy is x cubed over 3 plus x sin y minus e to the power of 2y equals to a c. Okay, now this is the solution for the differential equation, but we need to solve the IVP where y of 2 is equals to 0 given in the initial condition. Substitute x by 2 and y by 0 in this solution of the exact equation. So f of 2 is 0. So x is 2, y equal to 0. So we 2 cubed divided by 3 plus 2 sine 0 minus e to the power of 2 times 0 is equals to a c. So we need to know what this c is. Now 2 cubed over 3 is 8 over 3. Sine 0 is 0 minus e to the power of 0, which is 1. So 8 cubed over 8 over 3 minus 1 implies that c must be 5 over 3, and therefore the solution of the IVP is given as follows: x cubed over 3 plus x sine y minus e to the power of 2y equals to 5 over 3. So we have ended our discussion on the exact equation. That means this is the end of our lesson on chapter 2. So in chapter 2 we have discussed separable equations, homogeneous equations that can be transformed to separable equations, linear equations, Bernoulli equations that can be transformed to linear equations, and the last one is the exact equations. Thank you.